Great. Yeah, thank you very much for the invitation. So John mentioned in his last talk that there's this construction that that's called not contact topology, which gives you an invariant of just a smooth isotopy type of a knot, and more generally of some embedded submanifold. And so I'm gonna say a little bit more about what information we can get from this algebra. But before talking about not contact homology, let's maybe do a little bit of sort of run roughshod over a summary of the Chikhanov-Eliashberg DGA. Okay, which is some algebra that you get that's an invariant of a Legendrian in a contact manifold. So what is this object? Well, before I define it, I want to. So first of all, I have lambda is going to be some Legendrian in a contact manifold V with contact structure C. And I want to make some simplifying assumptions before defining it. Okay, what are my simplifying assumptions? Well, first of all, V is just going to be a one-jet space of some other manifold. So you know, you can work in a more general setting than this, but this will make things easier for me. My contact structure, kernel of a Warn form alpha, where right the one-jet space of M is identified with the cotangent bundle of M cross R. Say where that's a Z coordinate, and I can take alpha to be dz minus my tautological one form on the cotangent bundle of M. So notice that, so what this ends up meaning is that the Reb vector field associated to this one form, it's just in the Z direction, and so we end up getting no closed Reb orbits. Okay, and in the presence of closed Reb orbits, one has to set up a more complicated definition. I also want to assume that, so that's sort of all in the first assumption, and the second is going to be that I want my Legendrian to have vanishing Maslov class. Okay, so for a Legendrian in dimension, if this were a Legendrian link in dimension 3, this would be saying that the rotation number is 0. But in general, you have a Maslov class in H1 of the Legendrian, and I'm just going to assume that is 0. What this ends up doing for me is it ends up giving me a grading of my algebra over Z. Okay, once I do that, though, I am going to define my algebra it's going to be an algebra over the integral group ring of H1 of my Legendrian. There are some other versions that one could use over different rings, but we'll stick with this one. And this algebra is going to be freely generated by Reb chords of lambda. Okay, so we have a Reb vector field. We're just taking integral curves to the Reb vector field, which start and end on our Legendrian. And you know, I maybe need to perturb the Legendrian so that there's just finitely many of these. My grading, I'm just going to sort of punt, say that there's some sort of Maslov type grading. You define it by making a couple of choices, and and you're able to define it's called the Conley-Zander index, and this ends up being the Maslov index of some loop of Lagrangians in an appropriate complex tangent space, in an appropriate trivialization. So you're looking at a map from Cn to Cn. Okay. And then finally, the differential in this differential graded algebra. Well, what I'm going to do is I'm going to look in the symplectization of V. Okay, say I have an R direction that's given by T, and what I do is I'm going to look at, with a compatible, almost complex structure that's been chosen. I'm going to look at some moduli space of holomorphic disks such that when you go out to infinity, so past some sufficiently large interval, the image of this disk, really it's a disk where you've removed some points at the boundary, and a neighborhood in the disk of that puncture is being sent to a Reb chord across a half infinite end. And such a disk is going to contribute some element in the coefficient ring times B1, B2, B3, if this is appropriately oriented, to the boundary of A, where this U is supposed to be the name of my holomorphic map, and where CU, this is an element of my ground ring. What one has to do is one has to pick some capping paths. In the Legendrian, And then when you, oh, look what I've done. If I look at the boundary of my disk minus those punctures on the boundary, this needs to be sent to R cross lambda. And then there's some capping paths inside of lambda which complete this to give me some one cycle inside of there, and that's how I get this element inside of the group ring. Okay. So I wanted to do that to maybe save Pan some trouble. I should mention also that your grading, should be the grading of this product should be one less than the grading of the reb chord that's on the positive infinite end. Okay, and then this ends up giving you a well-defined differential. So it's a consequence of Ekholm, Etnier, and Sullivan that this differential squares to 0. And at least up to quasi-isomorphism and a more general notion of equivalence, actually, the algebra that you get with this map from the algebra to itself is invariant. Ooh, first of all, is well defined. There are a bunch of choices that were made. And but it's also an invariant of the Legendrian isotopic class of lambda. Okay, any questions or comments about that? Okay, so from this construction, we get this complex of algebras. And I'm going to be interested in what are called augmentations. Of my DGA. And I'll be thinking about fixing some field and thinking about what I'll call augmentations into that field. So in order to make this, I guess, seem sort of natural, what you want to do is for each generator of H1 of lambda, you want to choose some non-zero element in the field, and then this gives you a map And then this allows us to think of our algebra tensored with F as an F algebra. Okay, and then an augmentation is a map epsilon into F such that if I take my subalgebra and grading 0 tensored with F, and then I look at my chain complex above that, this should be exact. Okay. Well, so this tensor product is naturally an F of H1 of lambda algebra. And so now multiplication by each generator of H1 should correspond to just multiplication by this element. So just a comment about, okay, so my map epsilon is the augmentation into F. And just as a remark, if it happens to be the case that my DGA is supported in non-negative grading, okay, then augmentations into F can just be identified with homomorphisms from the degree 0 homology into F. Right? Okay. And so not contact homology is the DGA of a certain Legendrian, and you can set it up so that the DGA is supported in non-negative grading. So this will be the case in not contact homology. That's okay, so if you look at this algebra, it's maybe difficult to really understand it in its entirety, right? But the sort of history of using this object has, at least a lot of the time, you get something that's a lot more tractable by using these augmentations in some way. So one way in which this has been done is to look at something called linearized contact homology. and basically, if you're given an augmentation, the differential actually, it descends to the quotient algebra kernel of epsilon mod kernel of epsilon squared. And the linearized contact homology with respect to this augmentation of lambda is the associated homology. This is a little bit easier to work with because this here is now just a graded vector space. Okay. So now let's talk about not contact homology. Okay, and as John recently told us, if we have n smoothly embedded inside of M, then we can pass to the, say we pick some metric, then we can pass to the unit cotangent bundle over M. And what we do is, over the points in our embedding, we look at, sorry, John, I'm going to call it lambda n rather than ln. Okay, so we have this unit conormal lift. Which is just the collection of covectors which annihilate the tangent directions to n, which are in this unit cotangent bundle. And this is Legendrian in the standard context structure. By which I mean, right, the cotangent bundle has a canonical symplectic structure given by D of the Louisville 1 form. And so I look at that one form restricted to the unit covectors. and this is a contact one form on this on the unit cotangent bundle. Okay. And so then, not contact homology is, we'll write it as HC of n, and this is just by definition the homology of the DGA of lambda n. Okay. So, right, if you think about any smooth isotopy of this embedding, then that is going to lift to a Legendrian isotopy of lambda n. And so since this is an invariant of Legendrians, this is an invariant up to ambient isotopy. Okay. Great. And it seems to be a very powerful invariant, at least in the setting where we can actually study it currently. Right? This is a pretty complicated piece of machinery, but there's this really great theorem. By Ekholm, Etnayer, Lenny Ng, and Michael Sullivan. Where basically they show how to compute the knot contact homology for a link in R3. And the computation uses a combinatorial DGA defined earlier by Lenny. Okay. So let me just point out that it really is well defined in this setting. The unit cotangent bundle over R3 is contactomorphic to the one-jet space of the two-sphere. And our conormal tori have vanishing Maslov class. And as I mentioned before, you can take an appropriate embedding of the knot case so that the DGA is supported in non-negative gradings. Okay, so that's worth mentioning. You can generate in grading 0, 1, and 2. Also, because of the niceness of the contact one form, so the Reb chords are actually in bijective correspondence to oriented binormal chords of K. So what's meant by that? You have your link embedded in R3. If you have a line segment starting and ending on the knot that's oriented and which is normal to the tangent directions at both ends, then call that a binormal chord of K. And the Reb chords are in one-to-one correspondence with that. And in fact, you can get your hands on you can really treat at least some part of this invariant in a very topological way by allowing yourself to think of homotopy classes of paths which start and end on the knot, and each of these oriented binomial chords is in one of those homotopy classes, and this allows you to draw some connections to more classical subjects like the fundamental group. So this provides route to things like the fundamental group. thinking about some sort of homotopy class of paths beginning, ending on K. And it leads to a nice theorem of Lenny that the degree 0 homology is actually isomorphic to something that lives purely in the topological realm, the chord algebra. Okay. All right. So I'd like to tell you what the chord algebra is, but I think I maybe don't have the time to go really into the definition. But it's a really nice object. And using the fact that your augmentations just come from homomorphisms from this into your field F, you can use that to learn a lot about augmentations. And those are some of the results that I'm going to tell you about right now. I'm going to tell you about certain augmentation varieties. Okay, so this combinatorial formulation of the DGA what you do is you start with some braid, say in the n-strand braid group, with which as a closed braid is equal to the link. And then the Reb chords in grading 0 so basically as you think of your closed braid, sort of braiding happening here. You can find for each pair of strands an oriented binomial chord from one to the other. Denote that by Aij. This is binomial chord. J. Where those strands are just, these are inside of a solid torus that this is braided inside of. Then, so you have these generators Aij, and say, let's just sort of simplify a bit. Say that K is actually a knot. Okay, so then we can identify the ground ring with a two-variable Laurent polynomial ring generated by a meridional and a longitudinal class. And so then you have these generators Aij and the generators of the ground ring lambda and mu, which in which the differential for the algebra is completely expressed in terms of them. Right? So the image is an ideal generated by polynomials in these n times n minus 1 plus 2 variables. And this immediately gives you the structure of an affine algebraic variety. And just to produce some notation for that, I will call that variety V of K. All right? And you have the inclusion of your ground ring into your algebra. This produces a restriction map on the variety. Sorry for the lack of board space. But you have a restriction map, and so there's an associated variety to the image of that. So we'll call V R, which is a algebraic set inside of C2, the associated variety. Okay. Any questions about that? So now this curve inside of C2, and I guess we don't know at the moment if this is always a curve. It's always codimension 1 inside of C2, but that seems to always be the case. Maybe always. So we get a polynomial that is cut out by this curve. And by picking a normalization appropriately, we get a well-defined polynomial called the augmentation polynomial. It's non-trivial to compute this in general, right? Unless you are better than most at elimination theory. But it's actually related to some nice classical topological construction. So Lenny found a relationship to something that's called the A polynomial. Okay, so what is the A polynomial? I want to think about representations of my knot complement to SL2C. And I can always pick a basis here so that my Seifert longitude and meridian of my knot are simultaneously upper triangular. Right, because they commute. Then the A polynomial it cuts out the set of points M naught, L naught, which show up as eigenvalues for such representations. Okay, this was at least the way that the A polynomial was originally defined. And let's call this A polynomial A sub k. So then what Lenny showed in 2008 was that this polynomial is a factor of the augmentation polynomial if you just make a slight change of variables. Okay. So, and in fact, that there's maybe I forget at the moment if this is already algebraically closed or not, but the closure of this is actually some algebraic subset of this one right here. Okay. But often there are other factors. So let's explain them. So to do this, what you have to do is, so this mu squared is actually coming from, it would just be a mu if instead of looking at SL2C here, you looked at GL2C. That's not right. If you looked at GL2C such that your meridian has an eigenvalue of 1. Okay. And basically what I want to do is I want to think about a higher rank representation variety. So pick n to be at least 1. I'm going to define this set to be the set of representations into GLNC with the property that rho of m, I can choose some basis so that it just goes to this block matrix. Okay, for some meridian of the knot. I'm going to decorate this with an IRR if I'm just looking at those representations of this kind which are irreducible. And then I'll let our aug of k just be the union of all of these where let's say I just think about the irreducible ones for a reason I'll point out in just a second. So basically, by looking at this eigenvalue u0, I actually want it to not be 1. And the Seifert longitude has a corresponding eigenvalue because they share that one-dimensional eigenspace. You can actually recover all of the factors in the augmentation polynomial. And I'll write something that in the end ends up implying that this set of all such representations modulo conjugation is in one-to-one correspondence with POM HC0 to F. Yeah, so around 2014, I guess. So you can understand actually all of these augmentations in this representation theoretic way. I think that this is actually nice support for there's a conjecture out there that a more enriched algebraic structure on not contact homology, that it has an augmentation polynomial which is somehow, this isn't quite right, but it somehow controls colored Homfley polynomials of a knot. And there's a conjecture that occurred a long time before that called the AJ conjecture, which is supposed to relate the A polynomial to colored Jones polynomials of the knot in the same way. And I actually think that this is supporting the conjecture that the augmentation polynomial is really the right thing to be looking at for those colored Homfley polynomials. But in addition, there's a lot of nice things that you get out of this correspondence. One thing that you get is to each of your augmentations, you have an associated rank. Right? The n, each point in here is in one of these, and so that's your associated rank. And this actually, thinking about rank of these representations is actually a really useful thing to do. Let me point out that the rank of an augmentation is actually always bounded above by the number of meridians that you need to generate the knot group. Okay, you have some number of meridians generating this group. They each have some distinguished one-dimensional eigenspace. The smallest subspace containing those is an invariant subspace because of the definition of the defining condition for what it means to be in that set. And so, if you're interested in topological applications, this allows you to pinch the meridional rank and the bridge number of knots together. The bridge number of knots and meridional rank of knots has long been thought to be two things which are equal, and so I've been able to make some progress in that direction. I don't have much more time, but let me just, I'll say a few more things. So first of all, here's a question. The way that I end up defining this correspondence it's algebraic. And in particular, it leaves open the following question. If the DGA, sorry for changing my notation, for the conormal lift of some knot K1 is the same as the DGA for conormal lift of K2, so what this means is there's some stable tame isomorphism between these two DGAs, which induces an isomorphism on the homology. So you're able to, from an augmentation on one of them, you're able to induce an augmentation on the other from this. Does an augmentation on HC of K1 induced from one on HC K2 preserve the rank? For my initial construction, it's not clear, and I've got work in progress where this question would be answered in the affirmative. If so, then for two such knots, their A polynomials would have to agree. Okay, now there was some conversation before about whether this is really just going to say that the A polynomial of a knot is equal to the A polynomial of the same knot, or the A polynomial of its mirror, which would be probably which would be an equally empty statement. Okay, but I do think that there's still at least a little bit of question about whether you can have such an equality with two knots that are different. At least it still needs to be answered in the literature. Okay. You can do this with multiplicities, and I think you can use that to cook up. You can show that the knot contact topology detects the figure 8 knot. Okay. So just to end, because I'm pretty much over time, if you go back, so this whole time I've been looking at this restricted variety, the image under this restriction map. If you go back to the entire variety and actually maybe take some subset of it that passes through a certain nice quotient coming from an involution on the red chords, then some subset of this, interesting subset, this actually has a nice relationship to the SL2C character variety of the double branch cover over your knot. And in fact, the ranks play an extremely important role. The ranks of your augmentations. They tell you all sorts of information about the algebraic properties of the images of the representations that these are characters of when you look at the correspondence between these two objects. So maybe to say that, say a more concrete statement, for example, if any knot has an augmentation with rank larger than 4, then this character variety is not isomorphic to the character variety of, to the augmentation variety, this particular algebraic subset. And when you don't have any augmentations in rank 3 or 4, you can actually guarantee that the double branch cover is not hyperbolic. Because if it were hyperbolic, the geometric representation would end up having you send it through a map it has to end up going to something of rank 3 or 4, because you see the abelianness or non-abelianness of the image of the representation. Okay, that's it.